Hey everybody, welcome to day number 5 update for Honors Chem e-learning. Hope everyone's doing, great so far at home. For me, I just went shopping recently.
Turn down for what?
Well, that was weird. So for day 5, what we are focusing on is an experiment that I actually did at home for you. Normally, obviously, we would do this in the classroom. I normally thought this was one of my favorite labs to do besides titrations. I liked doing this reaction rates lab because what happens is there's some kind of color change that comes out of nowhere, and you'll see that with a bunch of, not a bunch, 2 videos that you're going to watch with the lab that I did. Normally, again, it takes about 2 full class days to get used to the whole procedure, but what's going on is that I'll be doing a bunch of mini reactions between something called potassium iodate. It is this clear solution right here, and something called sodium metabisulfite, which is this clear solution over here. Okay, nothing crazy. But what happens is it creates iodine. Now, normally iodine you really can't see in this reaction, but what I like to add to it as well is the starch solution. Now you can see that it's this weird, like yellowish, cloudy solution here. So if you remember in biology or just anything, at home you did with iodine and potatoes, it turns like a brownish, blackish, bluish, purplish color. I don't know, again, you're going to see in the lab it turns like a weird, like dark brown, black color, but iodine and starch is this very dark color. So, but the cool thing is that it takes a while for these two to actually create the iodine. It's very weird. The actual reaction itself is extremely complex. So I have in the document that if you are going to take AP Chemistry, you can probably learn more about it in AP Chem. But for now, we're focusing on just reacting these 2 things together to make this iodine. So you're going to see in the actual lab, I use little things called a well strip. You've used well plates before for previous experiments. These are little well strips. I just have a bunch of small, reaction vessels, you could say. And I just use pipettes and put like drops of each of these substances in these little wells. And I followed a grid, and I followed a certain like drop count number chart. And you can see that in your document. And you're going to basically see what affects, or how concentration and how temperature affects reaction rates. Now, I have a bunch of different trials for this because reaction rates are very similar to popping popcorn. Okay? When you eat popcorn, hopefully you eat, hundreds and hundreds of kernels. You don't just put one kernel in the popper and let it go. That's terrible. And if you put all the popcorn in your popper, turn it on, do all the kernels pop at once? Like, can you imagine how crazy that would be? Obviously, no, okay? Not all the kernels pop at once. So you'll have some that pop early. You'll have some that don't even pop at all, okay? But what you could do is that if you kind of averaged the time it took for all the kernels to pop, you would get a good average time for the average popcorn kernel to pop in your popper, okay? So that's kind of what I'm doing with this experiment. So I don't want you're going to see in the document, you're not going to time all 8 reactions in this little well plate, or this well strip, because maybe there's a couple that won't even go at all. Or maybe there's some that will take so long, okay? So it's not fair to include that. It's kind of like, if there's a gold medal race in the Olympics, the 100-meter dash, let's say the 8th place finisher falls and doesn't even finish. Well, it's not fair to include that person's time in the average time for the 8 runners, because if that runner didn't finish, then the time is unlimited because you never finished. So you can't include something that didn't finish in an average because it screws up the data. So I'm only going to have you average the first 4 that finish. Okay, and you'll see that in the document. Nothing crazy. It's just an update video. So more about reaction rates is that I also like to compare reactions to Legos. in general, Legos can be used to just like explain so much of chemistry. It's just a simple concept. So I got 2 Legos. This is also in your background. Now what I also have here is a Lego Voltron, Defender of the Universe.
Voltron, Defender of the Universe.
So what's cool about Legos is that you can't connect them in any particular way. Okay. Now the background question for the lab, one of the questions is, what are 2 things that you have to do in order to make a Lego brick stick to another Lego brick? Now it may seem like a stupid question, like duh, you just stick them together. Well, no, you don't just stick them together. You have to do something, okay? And there are 2 particular things. Number 1, you have to orient them correctly. Okay? You can't... I know it seems stupid, but no. Some people say, well, duh, you have to put them in the right spot. Well, yeah, that's what I'm looking for. So you have to orient them correctly. Oh, that wasn't enough. You gotta do one more thing, okay? Oh, that's not really sticking. You have to give them enough energy so that they actually stick together. This will never come apart unless I rip it apart, okay? You have to basically orient the pieces correctly and give it enough energy so that the pieces don't come apart. And that's how you make Legos come together. I know it seems super simple, but the same thing happens with atoms and molecules. Oh, cool. The same thing happens. You have to orient the atoms and the molecules correctly for a reaction to occur. But not just that, they need to be given enough energy to react. Okay? That's why you're going to see in the temperature part of this reaction, the colder the temperature, you'll see the rate change because it's colder. Okay, so hopefully in the reaction rate sim from day number 4, you saw that with the simulation, is that colder things change the rate, and hotter things changed the rate. Okay, so again, I like to keep things simple. So the simple way to think about this is that atoms and molecules are like Legos. In order for Legos and for atoms/molecules to come together, they have to be oriented correctly. So the molecule has to be situated correctly with the other molecule it's reacting with. And they have to be given enough energy so that they can actually form or break bonds. Legos, enough energy to make the 2 stick together. Atoms and molecules, same exact thing. Okay, that's how I build a Voltron over here. Enough energy to put a thing together. So, great.